4. 4.2 to 1 for each of the baseband signals, I, M, T, equals cos LOONT, 2, M, T. Sin 2000 NT, 3, M, T, equals cos LO00 NT cos 3000 NT, do the following. 2 cos 1000 JLT plus. A. Sketch the spectrum of M, T. B. Sketch the spectrum of the DSBSC signal M, T, cos 10,000 RRT. C. Identify the upper sideband, USB, and the lower sideband, LSB, spectra. D. Identify the frequencies in the baseband, and the corresponding frequencies in the DSBSC, USB, and LSB spectra. Explain the nature of frequency shifting in each case. 4.2 to 2 repeat prob. 4.2, 1 parts, A, B, and C, only if I, M, T, equals sin, lud, 2, M, T, equals ELTL. 3, M, T, equals ELT, I underscore observe that ELTLL is ELTL delayed by 1 second. For the last case you need to consider both the amplitude and the phase spectra. 4.2 to 3 repeat prob. 4.2 to 1 parts, A, B, and C, only for M, T, equals ELTL if the carrier is cos, 10, LO00T. RR/4. Hint, use EQ. 3.37. 4.2 to 4 You are asked to design ADSB-SC modulator to generate a modulated signal Km, T, cos, wet plus 0. Where M, T, is a signal band limited to Hz. Figure P 4.2-4 shows a DSB-SC modulator available in the stockroom. The Kennier generator available generates not cos wet, but cos 3 wet. Explain whether you would be able to generate the desired signal using only this equipment. You may use any kind of filter you like. A. What kind of filter is required in Fig. P 4.2-3? B. Determine the signal spectra at points B and C, and indicate the frequency bands occupied by these spectra. C. What is the minimum usable value of W? D. Would this scheme work if the carrier generator output were sin 3 wet? Explain. F. Would this scheme work if the carrier generator output were cos and wet for any integer NC:2? M. T. T at I filter copyright 2. A. B. Figure P.4.2, 6. Problems 197. 4.2 to 5 You are asked to design a DSB-SC modulator to generate a modulated signal Km, T, cos wet. With the carrier frequency Phi equals 300 kHz, W equals 2N, x 300, 000. The following equipment is available in the stockroom. I. A signal generator of frequency 100 kHz, 2. A ring modulator. 3. A bandpass filter tuned to 300 kHz. A. Show how you can generate the desired signal. B. If the output of the modulator is Km, T, cos wet, find K. 4.2 to 6 Amplitude modulators and demodulators can also be built without using multipliers. In Fig. P 4.2. 6, the input, T, equals M, T, and the amplitude AL, T, I. The two diodes are identical, with a resistance of R ohms in the conducting mode and infinite resistance in the cut-off mode. Show that the output E0, T, is given by 2R. E0, T, equals dash, W, T, M, T. R plus R. Where W, T, is the switching periodic signal shown in Fig. 2.20 A with period 2n/w seconds. A. Hence, show that this circuit can be used as a DSB-SC modulator. B. How would you use the circuit as a synchronous demodulator for DSB-SC signals? R. A. B. 4.2 to 7 in Fig. P 4.2-6, if T equals sin, wet plus 0, and the output EO, T, is passed through a low-pass filter. Then show that this circuit can be used as a phase detector, that is, a circuit that measures the phase difference between two sinusoids of the same frequency. Hint, show that the filter output is a signal proportional to sin 0. 4.2 to 82 signals M1, T, and M2, T, both band limited to 5000 Hz, are transmitted simultaneously over a channel by the multiplexing scheme shown in Fig. P 4.2-8. The signal at point B is the multiplexed signal, which now modulates a carrier of frequency 20,000 Hz. The modulated signal at point C is transmitted over a channel. A. Sketch signal spectra at points A, B, and C. B. What must be the bandwidth of the channel? C. Design a receiver to recover signals M1, T, and M2, T, from the modulated signal at point C. 4.2 to 9. The system shown in Fig. P 4.2-9 is used for scrambling audio signals. The output Y, T, is the scrambled version of the input M, T. A. Find the spectrum of the scrambled signal Y, T. B. Suggest a method of descrambling Y, T, to obtain M, T, 0.198 amplitude modulations and demodulations. Figure P.4.2-8. Figure P.4.2-9. Figure P.4.3, 1. Figure P.4.3-2. BC. A. 5000 J- plus 2 cos 40,000 NT. 2 cos 20,000 M. A slightly modified version of this scrambler was first used commercially on the 25-mile radio telephone circuit connecting Los Angeles and Santa Catalina Island. M. F. 2 cos 30,000 NT. Low pass filter 0 to 15 kHz. Y. T. Scrambled output 4.2 to 10. A DSB-SC signal is given by M, T, cos, 2RR, 106T. The carrier frequency of the signal, 1 MHz, is to be changed to 400 kHz. The only equipment available consists of one ring modulator, a bandpass filter centered at the frequency of 400 kHz, and one sine wave generator whose frequency can be varied from 150 to 210 kHz. Show how you can obtain the desired signal. Cm, T, cos, 2RRX 400X to 3T, from M, T, cos, 2RR, 106T. Determine the value of C.